everybody, today we're going to talk about some obscure, arcane knowledge that writers don't understand a bit. We're going to be talking about math. Math is the short version of mathematics, and I'm pretty sure that if you write or if you're involved with the art field, you probably made some kind of joke being like, oh my god, I hate math. Math is so stupid, math is so boring, oh my god, I only work with liberal arts, I don't understand math at all. Unless, of course, you're a video game designer or a writer for the TV show Futurama. I have seen many writers have many problems with some simple math concepts that kind of piss me off actually. So I am going to give you a quick review of some useful math concepts that you can use in your writing. So, when we talk about math, there's actually two types of math that we need to consider. One type of math is the math that you learned in school. You know, when you have to memorize your multiplication tables and that apparently scarred you from trauma so much that you can't comprehend math anymore. Yeah, that's the numbers math. We have, 7 plus 7 equals 49, 7 plus 8 equals 56, 9 plus 9, 9 times 9 equals 81. Yeah, and there's the math that is an actual language of logic. When you write something like a plus b squared equals a squared plus 2ab. This means something. The symbols that I have written mean something. These symbols that you see written, they actually mean something. And this is something that I think that many artists, many people of the humane sciences aren't able to understand. And this is probably what brings, the most confusion over math. I won't be explaining everything, only the basics. But before we start, let's talk about the numbers math for a bit, because there's something that kind of bothers me, When you see a scientist in a work and the scientist doesn't understand the scientific method and starts experimenting on everyone, dude, you need a control group. Who taught you how to science? Anyway, there are many things about our number system that we take for granted, but if culture or if humans had evolved a different way, they probably would be very different than what we understand. For example, the number 10 is really important today. We always talk about the 10 commandments, the 10 rules for something. Why is 10 so important? Well, it's mostly because we have 10 fingers. So if I wanted to count something, I could count like this. Because of this, 10 ended up being kind of the basis of our number system. This system of base 10 is what we use to count and to write numbers today. Let me give you an example. When I wanted to write a number and the number is this, notice how I put every single number in each space. This is because we work with the base 10 system. So if I were to write this number and say it out loud, it would be 1567. Because this is what those numbers are. We divide the numbers like this because our system is base 10. Technically all systems are base 10, but we don't need to discuss this today. So if you were, say, writing a sci-fi where there are aliens and with other cultures, with other anatomies, they probably wouldn't follow base 10. This is something to consider when you're writing, intergalactical mathematical standards. Even here, in our world, our real world, we use systems that aren't necessarily base 10. For example, if you're going to count the seconds in a minute, it's not 100 seconds, it's 60 seconds to 1 minute, and 60 minutes to an hour. That is base 60, that is not base 10. And you also need to talk about binary. You know what binary is? Because a lot of people don't. See, binary is how computers communicate, because like you have a wire in your computer and that wire goes to the motherboard or something. The wire can only be in two states. It can either be on with electrical current or it can be off. There's no electrical current passing. So because there are only two states of being for this wire, so they end up adapting. So I have these wires and they represent numbers. If I were to say represent the number 15 here, I would go electrical current on this one, electrical current on this one, electrical current on this one, and electrical current on this one, because these together equals 15. If I wanted to write 14, then it's just not current here. This would not be represented, would be a 0, so it would be 14. If I wanted to put 13, so I would put a current here, no current here, so it wouldn't be represented at all. And this one, because there's a current, then it is 13. It is 13 here. So this is a basic binary system that computers use, and if you didn't know what binary system means, so now you know. Enough of numbers math, let's talk about logic math, the math that is essentially a logical language for you to be able to derive the consequences of a certain statement. And the statement that we see a lot in math looks something like this. This is a function. This is essentially the same as an equation. It's called equation because there is an equal sign here. So if you are one of those writers that are just so humane and they hate math, you probably don't understand what this is. It looks like a foreign language to you. Well, what you need to understand is that this equation is kind of like a machine. A value comes in and another comes out. So if I were to put anything here, this anything would be transformed into this. This circle ends up being transformed into this. This is what an equation is. A star comes in and out comes star squared plus 2 times star plus 1. This is what an equation is. So if you're going to create an equation, you're basically creating something like, oh, you put something in and another thing comes out. Let's say, oh, I want to see the speed of this car, and went from here to here in this many seconds. So there's an equation, you put this space there and you manage to come up with the speed. So if you're going to write an equation, let's say, I don't know, you're writing a poem or something, an equation for love, then I suggest you do this. You divide the board into 2 segments, positive and negative, and you see what positively impacts the thing and what negatively impacts. Say, you're going to build the little cogs in the equation machine. So here when you're going to be putting pluses, obviously, and also times, and when it diminishes, you're going to be putting minus and also divisions, because those are things that makes numbers smaller. And these ones have to do with proportions, and this one has to do with a constant. So let's say that you're writing an equation for love, and you're thinking about, okay, so something that makes me love my partner more is when he buys food to me. So let me, it's a little hamburger here. Have you bought food for your girlfriend today? Because she would probably really enjoy it. Think about it. So, does the food is a constant, which means that 1 hamburger gives a value and 2 hamburgers gives 2 times the value, 3 hamburgers are 3 times the value? Or does this have to do with proportion, which means that the amount that the hamburger is going to affect the equation is also depending on the proportions on something else. Let's say my hunger. The more hunger I have, the more the hamburgers satisfy me, and the less hunger I have, the less hamburgers make me love you, essentially. When it's a constant, the hamburger constant does not change, it is a constant. But if the hamburger is dependent on the proportion of something else, then we can write this as a fraction, which means the fraction of hamburgers and hunger. Okay, this is getting a little confusing. Let me try this. I am explaining what fractions are now, just so we don't get confused on what exactly is going on. A fraction is a measure of proportion. As you were talking, we have the example of hamburgers and how hungry I am. So if the amount of hunger and the amount of hamburgers increase in the same proportion, say let's times 2 for example, things essentially stay the same because I'm twice as hungry but I have twice as many hamburgers, so this doesn't matter. It only raises or declines when the numbers are different, essentially. So if hamburger was a constant, if I were receiving 2 times as many hamburgers, I would be 2 times as happy. But if hunger is in the picture, if I receive 2 times as many hamburgers, that depends on how much my hunger has increased or decreased. Because that's what a proportion means. Because it doesn't matter the value by itself, it also matters combined by something else. You can actually see a lot of funny ways that proportion is actually used to mislead us. Because someone can go and say something like, hey, here's the amount of crack users. And crack users say that 80% of them started with cannabis. This is something that I just made up, but it's an argument that can happen. So you think about it, oh, 80% is such a big number. So probably cannabis is a danger to public health because 80% of crackheads started as cannabis smokers, cannabis enjoyers. But then you remember that the amount of people that smoke cannabis is much, much bigger. And this number that seems so big doesn't seem that big at all under the proportions of the amount of cannabis smokers. This is something that they can use to manipulate you. Do you know what else they can use to manipulate you? Statistics. Let's talk about that. So you probably know that averages aren't exactly the same all the time. Because let's take, for example, a number, 12. Because let's say we have an average of 12. You can do this by having, 12 plus 12 over 2. That means that the average is 12. But you also could have 0 plus 24, 2 equals 12, or 5 plus 19 over 2 equals 12. You could have many configurations. This is called a standard variation. What is the standard variation? Let's put this on a graph. And let's say that this example here, everyone is pretty much on the same level and they get averaged into this. But what if they are like this and they are more spaced out? Well, this is the standard variation, I think. I don't actually know the name in English. Yeah, so not all averages are the same. Do you guys know what this is? Yeah, you probably saw memes about this. It's called the normal variation. Usually data when collected usually looks like this, not always, but don't worry about it. You don't have to worry about any other distributions. The normal distributions basically means this. There is going to be a certain amount of people that are going to fall into the average, into what the average person does, but a lot of people are going to fall here, not necessarily in the middle. There are standard variations and everything. A very common statistics problem is you have a machine produces X screws per day, and the screws need to be under this amount of size. And seeing that there is a probability of mistake of X%, what's the probability that Y amount of screws is completely worthless? So you need to calculate the probability of it ending up here and ending up here. One last thing that I would like to mention about statistics is something called the large number theorem. I think, I don't know the name in English. What this means is essentially this. The higher the number of your sample, the more likely that it's going to follow into a graphic distribution like this. Because if you pick someone random on the street, they can be anywhere, in here. It's more likely that it's here, but if you pick like a sizable amount of people, then it starts acting similar like this. But if you pick up only one person, it's just a dot. You can't actually do the graph. But the more people that you pick, the more the sample starts resembling the distribution graphs, which is called the theorem of large numbers, and this is why sample sizes are very, very important. And since we're talking about statistics, why don't we talk about probabilities too? This is probably the most important part of the video. So let me tell you exactly how you calculate a probability. Let's say a fair coin, a coin that has heads or tails and have the same probability of being either head or tails. Then you have two probabilities, half and half, because probability is only one. One is 100%, And since there are two probabilities, there is half for each, half probability. So you can also say that the probability of this is the probability of one minus the probability of the other event happening, which in this case happens to be a half, but not always. When you talk about probability is very important in game theory. Game theory is, a part of math that everybody seems to like to talk about, so let's talk a little bit about it here. How do you represent a game in math terms? Well, you can either represent them as a tree or as some tables. Let's say that, you're playing rock, paper, scissors, so you can pick three options: rock, paper, scissors, and player 1. Player 2 can pick between rock, paper, scissors. If player 1 plays rock and player 2 plays paper, then player 1 gets nothing and player 2 gets 1 point, and the inverse happens. You can write a game like this, or you can write it like a table. So you have, here is player 1, here's player 2. You can write it either as a tree or as a table, because here, analyzing this branch. If player 1 plays rock and player 2 plays rock, then no one gets a point, but if he plays paper, player 2 gets a point. If he plays scissors, player 1 gets a point. This is essentially how we write games, and there are many games that we can talk about. There are games that are zero-sum, and there are games that are not zero-sum. What zero-sum means is that the amount of winnings that you can have is essentially zero. What this means is that for you to get something, you need to take something from someone else. This is a game in which all the points you need to take from a player. But there are games that you can actually get points by collaborating with another player instead. Those are non-zero-sum games. And you can actually arrive in something that, if you're writing a really smart and really obnoxious character, you can tell him about Pareto efficiency, which essentially means this: nobody in the game can win something unless they're taking from someone else. Because let's see a representation of resources. Okay, wait, that's too complicated. This is let's say there are 100 trees in a forest, and there's you and me. If I have 70 trees and you have 30 trees, the game is at Pareto efficiency, because I can get any more trees without taking from you, and you can't get any more trees unless you take them from me. But if we say, oh, 40-40, the game is not at Pareto efficiency because there are still 20 trees left in the game. It's kind of like Monopoly, you know. Monopoly has all the streets, all the terrains that you can buy, and it comes to a point where the game is not operating at Pareto efficiency at first because there are still terrains that are free and no one has taken them yet. The game is not running at Pareto efficiency. But then there comes to a point where all the squares are bought, but they're not actually allocated at maximum efficiency. Because let's say I have 2 of the red terrain and you have 1 from the red terrain, and I could trade with you and for you to complete another color for you to make a hotel. Which the allocation of resources is actually complete, and you actually need to take from other players falling on your square. You can't trade yourself and mutually benefit each other anymore. So if you have like a really obnoxious genius character, you can talk about this. You can also talk about Nash equilibrium. Nash equilibrium is basically what we do at Game Theory 101 classes. Let's say we have a table with player 1 and player 2. Let's review the possibilities. Player 1 can play A, B, or C, and the same for player 2. If you actually see at this, there's no reason why player number 1 needs to play move B, because it's the worst one out of every choice, because 2 plays A is the worst one, if 2 plays B is the worst one, if 2 plays C is the worst one, so there's no reason why you should play B. Then player 2 looks at it and says, well, player 1 is not going to play B. So there's a reason for me to play C, because C I don't get anything, only on the case where they play B. So I won't play C. And player 1 looks at it and say, oh, since they are not playing C, guess I'm going to not play A, because... And so it goes. This ends up being in the Nash equilibrium, in which every single character takes into account what the other character is planning on doing, and they end up reaching an equilibrium in which the obvious one should be played is this one, because we know that 2 isn't going to play A in the situation. So well, that's it. That's my math course for writers. And then I have looked a little bit, too abstract, but there's only so much I can do with pure math. If this were an economics for writers class, I can guarantee that this would look very different. But I also like the fact that I managed to go through a certain concept with you guys, because you need to understand that math is a language of logic, and you can actually use it to represent many things. I do recommend you to look into what is needed for a book itself, because depending on if you're writing a sci-fi alien story or some kind of gambling manga, the math is going to be different for each of your needs. But I hope that this provided a guideline so you can actually write math a little bit more efficiently. Thank you very much.